Okay, so it's a great pleasure to introduce the speaker, Dalila Pirvu. She's a PhD student at the Perimeter Institute and the University of Waterloo, working with Matt Johnson. And she will be talking about bubble clustering in cosmological first-order phase transitions.
Thank you, Silke, and thank you for having me in this seminar series. I will talk about work that was published in this paper here, together with my advisor, Matt Johnson, and our collaborator, Jonathan Braden. So this talk is mostly centered around this video here. So this is what a relativistic first-order phase transition looks like. So I will introduce this phenomenon. I will explain how from this initial smooth background field, we get nucleation of bubbles, and these bubbles are, in this particular scenario, in this particular field theory, of two types. They either decay to a lower field value or a higher field value. I'll explain it in a lot of detail. I will then introduce a technique about how we simulate this phenomenon in real time. This is a new method, and it's very useful in practice. The main result that we obtained using this technique was to show that these bubbles did not actually form completely at random, but rather there is a correlation between them. And then I will touch on how we might use this pretty interesting result to learn more about quantum mechanics and the usual approximations that we use to describe this phenomenon by implementing this in an experimental setting. Okay, so what is a relativistic first-order phase transition? It happens when we have a theory with an associated potential that looks like this. So it has at least two non-degenerate minima. So if our system is initially located in this state, the false vacuum state we call it, it is not in the lowest energy state that it could find itself in. So it would like to minimize its own energy. And to do this, it has to overcome this potential barrier, and there are several ways for it to do so. You could imagine adding some energy into the system, in which case you could get this phase transition classically as well. Or you could imagine that the phase transition is triggered by fluctuations around this false vacuum state. And the fluctuations can be of several, many different types. In particular, they can be vacuum fluctuations or thermal fluctuations, etc. Now, when the field transitions into this lower energy false vacuum state, it does so locally at the point. So at random somewhere in the space, you get this new field, new phase of your theory, which, like I said, it has a lower energy density. Therefore, it has to be separated by the by the rest of the field by a domain wall. So this is what we call a bubble. So to sum up, a first-order phase transition involves bubble nucleation. Now, this is a phenomenon that is very useful and interesting for cosmologists because it happens to, it is a great candidate for explaining various stages in the thermal history of our universe. Most notably, I would say it's a candidate for explaining inflation or diagenesis, and more recently, we think that the Higgs vacuum today could be in a false vacuum state that at one point might decay to a low energy state. So, lots of things to be excited about. Okay, now when we say vacuum decay, we refer to a particular type of first order phase transition, namely the one where bubble nucleation is triggered by quantum 0-point fluctuations. So here, once again, I have a photo of these bubbles that appear in the space and begin to expand. And as time goes on, if we are in flat Minkowski space, then the bubbles will eventually take over the entire space. And this is when we say that the transition has been completed and the entire field is in this lowest energy state. This is a non-perturbative phenomenon that happens only in nonlinear quantum field theory. So of course, our analytical exact tools that we usually employ in quantum field theory or fail are not applicable to describe this phenomenon. Instead, what people have done is they, in particular, Coleman and his collaborator, they came up with this method that is now known as the Euclidean instanton formalism, where they interpret vacuum decay as an application of quantum tunneling from non-relativistic quantum mechanics. And they generalize it using various applications into field theory. And this is a very practical framework because it computes observables such as decay rates and the typical bubble profile. So more in detail. It proceeds, this formalism proceeds in analogy to the WKB approximation. And the dominant contribution to the dynamics, the path integral, comes from the classical solution, the Euclidean saddle point approximation. Here we have the equation of motion for the field. Notice that this is written in terms of Euclidean coordinates in n dimension. And the solution to this equation of motion looks like this. It interpolates between the false vacuum and the true vacuum under some predictable boundary conditions. And this rapidly transitioning region here we call the bubble wall. And the shape of the solution depends entirely on the shape of the potential. The decay rate has this expression here. The dominant term is in this exponential, and it is given by the magnitude of what we call the bound solution. So this is the classical solution to the equation of motion, and fluctuations enter this derivation as a prefactor. And similar to the WKB approximation, this is a first quantum order approximation to the full result. To obtain the Minkowski space bubble solution, what is done is that they analytically continue the Euclidean solution. And I'm plotting here the results. So here we have the bubble that appears out of nowhere with a critical radius. And it begins to expand. You see, this is, I'm plotting this in space versus time. So the bubble is produced at t equals 0 with this fixed initial size, and then the wall proceeds to expand. It accelerates until it reaches the speed of light and moves on to infinity. So the trajectory of this wall is follows a hyperbola. And again, we see outside of the bubble, we have the false vacuum. Inside, we have the true vacuum. So there are several approximations in this framework. Although it is useful for computing, again, these observables, it works in a highly constrained setting. For example, it imposes a very strong symmetry requirement on the solution, on the bubble solutions. It also assumes that fluctuations play only a secondary role. We know nothing about what happens during the nucleation process. We simply find a bubble that expands starting at a finite positive radius. Another impracticality is that it assumes all bubbles are formed at rest. But most importantly, there is an explicit step in the derivation which assumes that these bubbles are uncorrelated. They are rare and spaced out. However, we know, well, intuitively, these bubbles would be large, macroscopic, nonlinear structures that appear out of a smooth, homogeneous initial state, out of the vacuum. So there is another instance in cosmology, in observational science, where we know that large nonlinear structures are in fact correlated and not at all spaced out and independent of one another. And this is the case of galaxy biasing. So what galaxy biasing is the observed fact that luminous matter in the universe is not distributed according to the expected density based on the amount that we observe, but rather it traces an underlying density, an underlying massive field, which is the dark matter field. And here is the illustration of what I'm talking about. So the dark matter field is this dark web. It exists everywhere, but it clumps up in certain spaces, and at the center of these, they're called dark matter halos, we see luminous matter. So galaxies, in fact, correspond to peaks of this dark matter field, and we can infer the statistics of the underlying field from this measurable two-point function, the two-point correlation function of the galaxies. And there is a semi-analytic framework that explains this phenomenon. It was developed by Bardeen et al. In their seminal paper, and the framework is based on Gaussian peak theory. So you can show that these Gaussian fields are fully characterized by the statistics of their extrema points, the minima and the maxima in the random field. And you can show that the rare peaks cluster. And in the statistics of this clustering, of this correlation function, you can encode the power spectrum of the underlying field. You can fully describe the underlying statistics by looking only at the distribution of peaks. So here is an example of a realization of a two-dimensional random Gaussian field. And here on the left, I'm just taking one slice through this two-dimensional surface, and I'm looking at the amplitude of the field. So we see that this field is centered around 0. All of the modes in the Fourier decomposition of this random Gaussian field are interacting. They form these peaks, and if we set the threshold along the phi axis here, and we measure the number of peaks that are larger than the set threshold, what we find is that the ones that survive the selection process tend to be clustered rather than uniformly distributed. I will talk a bit more about this later. So, okay. We have this, we have the experimentally known fact that peaks are sites of formation for nonlinear structures. And bubbles are also large nonlinear structures. Therefore, we would like to know whether bubbles themselves could be correlated, if they could hold the statistics of the underlying false vacuum initial state. And if that is indeed the case, then we could, in principle, measure this in a lab, in an experiment, and well, this would be very interesting. But in order to do this, we need a completely new framework, since, as we were saying earlier, the classical mathematical framework for dealing with vacuum decay would be unable to, it is constructed in opposition to this observation. So we come now to this new technique that was developed by Jonathan Braden and several members in this audience. And this is based on the fact that in quantum mechanics, one can model the phase space evolution of a system using the Wigner function. So as long as this Wigner function is positive definite, it is entirely analogous to a classical probability distribution. And its dynamics is given by what is called the Moyle equation here on the left-hand side. It is exactly equivalent to the Schrodinger equation. So, of course, we're working with fields. We can just generalize the Wigner function to a Wigner functional. And the matrix elements are now of the density operator would now be computed in the eigenbasis of the field and conjugate momentum operators. The time evolution for any given configuration is obtained from the Wigner functional in a standard way. So you create an ensemble with an initial conditions drawn from this distribution given by the Wigner function. And then you time evolve using the classical Hamiltonian. And at a later time, you can recover the phase space distribution by averaging over an ensemble. So you would essentially be averaging over the Wigner distribution. And this is the expression of what an observable looks like in this framework. So here, when we're averaging, for example, the field and the momentum at later times, what we obtain is their classical expectation value. This is like a particular, as a generalized case of the Ehrenfest theory in quantum mechanics. So the time evolution master equation looks like this. The initial state is this Wigner functional here. It encodes the leading quantum perturbations. The classical evolution is given by the classical equation with motion, whereas the higher order terms would be included as a perturbation series. In practice, we don't actually look at these higher order corrections, and we only evolve classically. So the initial state, this Wigner distribution, is positive definite in the Gaussian case, which is what we will be working with, the vacuum state. This evolution, as you see, is exact, is no longer perturbative if our potential is quadratic, because this term here doesn't exist. And once again, the Wigner functional itself encodes the quantum effects to first order. In terms of implementation, we do this using a spectral code in one dimension, where we construct the field as described on this slide. So we linearize around this mean value, which, what we are eventually looking for is that the mean value is going to be the false vacuum. We have this field of fluctuations here, which is the field to be quantized in this framework. The fluctuations are sampled from the Gaussian distribution to obtain the vacuum, and the power spectrum is chosen to correspond to that of a relativistic massive scalar field. Just as a small comment, in our work here, we choose the mass to be the bare mass in the potential, the curvature at the false vacuum, but there are some subtleties here related to what the correct mass would be that accounts for renormalization effects on the lattice. So this is actually very interesting work that will appear on the archive, I believe, later today. It's by Jonathan and collaborators. So this is the Fourier decomposition of the field. And what this code does is that it involves each of these spectral modes under the classical equations of motion with just about any potential choice that you want. So this Wigner approximation is exact for the case of Gaussian fluctuations, where the Wigner function is positive definite, and for the free field, because there are no high order h-bar² fluctuations. So we should recover the full statistics of the free theory at any point in the time evolution for our field. And we tested this, and indeed, this is what we got. We recovered the 2-point statistics and the peak correlation function and distribution. In particular, for the peak correlation function, we compared the analytic expression that we obtain in terms of spectral moments. This is computed for the one-dimensional case. So what we show here is that the correlation function psi is a function of the separation between the peaks, r, and divided by the number density of peaks on a particular slice. So we take an equal time slice of our field. We count the number of peaks on the particular slice. Then we impose a threshold, see how many peaks are above this threshold, and then we compute the ratio of their number densities. This is the estimator that we use for the lattice in this expression down here. The analytic expression, I'm sorry, I should have mentioned, is computed in terms of the spectral moments of the distribution. So the spectral moments are in terms of powers of the power spectrum, and they fully describe this Gaussian statistics. This is a well-tested analytic result. So in this figure here, I'm showing the comparison between these two estimators. You can see the dots are the results from simulations, whereas the dotted curve underneath is the analytical prediction for 4 choices of peak height, of peak threshold. And the correlator is negative at very low separation equal to the smoothing scale R0. This means that there are no peaks to be found at separations lower than the smoothing scale. This is to be predicted. Then there is an exponential increase here. We see that the correlation estimator peaks at separations of a few times the smoothing scale, and then it begins to fade as we increase the separation. This tells us that there is an increase in the number of expected number of peaks at this particular separation, whereas at larger separations, we expect there to be fewer peaks. I should mention that a correlator equal to 0 implies that the peaks are uniformly distributed. So rather than being, uniformly spaced out, as perhaps intuition would dictate, the peaks tend to clump up together, and the rarer the peaks are, so the higher the threshold, the more clumped together they are, the more clustered they are. Okay, back to vacuum decay. We changed the mass term in the free theory that we used to evolve the Gaussian state, and now we employ this potential here that looks like this on the top figure on the right. It has alternating series of false vacuum and true vacuum at different multiples of pi. So the choice of this potential, as I will explain a bit later, is actually motivated by applications in with Bose-Einstein condensates. Now, because of the nonlinear nature of this potential, the evolution of these modes, the modes that are initially in this Gaussian state, they don't talk to each other. They begin to conspire such that the fluctuations that give rise to peaks grow until a peak will eventually form large enough to overcome this potential barrier and fall into the true vacuum potential well. And if it meets the right conditions, if it is wide enough and tall enough, it will stay there to form a bubble. So, okay, this is a pictorial representation of this process. I'm taking here a snapshot of the field, field amplitude function of lattice position. So, and I'm plotting here different snapshots of this field at equally separated time instances. So we start with the field in this green, dark green instance, and then as we let time flow, we see that the peak originally here, it moves, it travels across the lattice, in this case to the left, and then it grows. Eventually, when it reaches the 2 pi amplitude, so this corresponds to the depth of the right-hand side true vacuum well, it begins to expand, and it will expand until eventually it engulfs the entire lattice. So from this observation, just empirically, we see that peaks are forming, that bubbles form from peaks in these vacuum fluctuations. So once more, we ask ourselves, do they cluster? And we will show that they do. Now, the important parameter that determined the amount of clustering, if you remember from the free field case, was the detection threshold. So to compare our results, we choose 3 detection thresholds here for the size of the bubble at nucleation, and we will compute 3 different correlators corresponding to these 3 thresholds and compare our results. Of course, we see that there are 2 choices of true vacuum, and this will motivate us to look at the correlation function between bubble nucleation sites of bubbles that decay to either side, or oppositely between bubbles that decay to opposite wells, true vacuum states. Okay, so the most important length scale, the baseline length scale for a correlation function is going to be the critical bubble size. This is the bubble size that in the Euclidean instance of formalism gave rise to a bubble that could expand, that could undergo accelerated expansion rather than collapse back onto itself. So in order to obtain this bubble size in our simulations, we go through this procedure here. We keep the same setup for the same parameters for our potential. We single out individual bubbles on the lattice. And then we noticed in the previous slide that these bubbles are traveling across the lattice. They're not stationary. So in order to compare apples with apples, we're going to have to Lorentz boost them back into their center of mass frame. So we found a method to do this. And once they're all in this, once all of the bubbles are at rest with respect to one another, we average over the ensemble and obtain this average bubble profile here that parallels the one we obtained in the Euclidean instance of formalism, and we assign the critical bubble size R to half of the full width at half maximum in this average bubble profile here. And we see that this critical bubble has an average height, and this height will be key to us choosing the detection threshold. This is what our simulations look like. We try to maximize the number of bubbles that are formed in any one ensemble in order to minimize statistical errors. I'm plotting here what our detection algorithm detects for 3 different choices of threshold. So our field starts off around the false vacuum at pi. It is Gaussian distributed. And then these nonlinearities in the background field will grow until bubbles form. And this motivates a pretty simple, I would say pretty intuitive detection procedure. Well, first, of course, we need to get rid of the high frequency peaks that pollute the signal. So we apply a Gaussian filter. The filter has to be necessarily smaller than the critical bubble size, such that we do not obscure the very quantity that we're trying to obtain. Then on these smoothed slices, we detect peaks above our choice of thresholds that are written here. And then we look to the future of these peaks and see whether their light cone lies entirely in one of the true vacuum potential wells. If it does, then we say that the original peak that we found is indeed the nucleation site. So of course, with this procedure, we had to come up with an empirically, with an ad hoc definition of what the nucleation site is. I think this is part of the procedure for obtaining this correlation function, and different algorithms. For example, even increasing this detection threshold will of course change what is defined to be the nucleation site. All right, in terms of errors, we computed these by eye. We checked whether, I checked whether I agreed with what the detection algorithm was deciding. And I found that there were 2 main sources of errors that would give false detections, false bubble detections. First of all, you could have a large background fluctuation, such as here. This is a large background fluctuation hidden outside of or hidden in the vicinity of a nearby bubble that mimics a bubble, but is in fact not. It dissipates. And you could also have that algorithm detects bubbles along the walls of bubbles that have already been accounted for. So for example, this red triangle detector, I'm going to call it the orange detector, has assigned a bubble over here, but later on that same detector says, oh, actually, there's another bubble to the edge of this, but no, I think by eye, it is pretty obvious to see that they're in fact talking about the same bubble. So this happens. We estimated that roughly 5 to 8% of the detected nucleation sites are false positive events. These can influence the correlation function. So we did not include this effect in our error bars, but we think it should be pretty small. Another type of error is when you miss out on bubbles. It's not, it's the opposite case. You get a false negative, but almost without a fail, these happen at very, very small separations from bubbles that have already been accounted for. So the process that you can imagine is that 2 tall peaks are headed towards each other, and they collapse and they form a bubble. Well, sometimes both peaks are measured to be nucleation sites, other times only the end one is. But again, this doesn't increase the correlation. If anything, it probably works against our claim. Okay, and this is the result for the bubble correlation functions. Here we have the correlation function between bubbles that decay to the same well, the same true vacuum well. Here is the correlation function of bubbles that decay to opposite correlation, opposite well. So if I have a yellow bubble somewhere, and what is the probability that I find a blue bubble at a particular separation? And And this is what is shown in this middle panel here. And in the bottom, we have the correlation function between all bubbles. So this is the overall two-point function. The estimator, I'm showing it on the left, is defined in analogy with the peak correlation function. So this is the number density of bubbles at a particular separation within a particular interval on the lattice with respect to the overall number density of bubbles in the particular realization, or in that realization. And again, this is shown for 3 different detectors. And we see that even the detectors amongst themselves agree to a good amount. The error bar here, like I was saying, it doesn't take into account the false and the false positives and the false negatives. It is only a measure of the root mean square of the statistical uncertainty in our ensemble. So it scales in amplitude as 1 over the square root of the number of simulations in the ensemble. The parameters I might have not mentioned, I apologize. So phi naught adjusts the amplitude of fluctuations in the scalar field with respect to the size of the potential around the false vacuum. Lambda modulates the depth of the false vacuum well, and R naught is the width of the Gaussian filter, which once again is less than the size of the critical bubble. The critical bubble is R here. We ran this, we computed the correlation function for, I think it was 3 combinations of phi naught and lambda. In all cases, we obtained that the 2-point function was amplified in a region that corresponded to a few times the size of the critical bubble. So back to our peak estimator, we obtained the prediction for the estimator on an equivalent realization without the false vacuum potential, and this is what the dashed dotted curves here show, whereas the solid curves with the error bars are from the bubble correlation function, and the colors correspond to the same detection threshold. And we see that qualitatively they have the same feature. So if the peak correlator begins to increase exponentially immediately after at separations larger than the smoothing scale, the bubble correlator begins to pick up on separations larger than the characteristic size of the bubble of nucleation. So this makes sense. The peak in both cases is of order a few times this characteristic scale, and then we have the decay. While for the peak correlation function, there is a great sensitivity to the detection threshold. For bubbles, this is not the case. So because all of our detection thresholds are larger in amplitude than this, than the amplitude of the bubble at the critical at nucleation, then this is a nice confirmation that the detectors are all looking at the same thing. So they are not, they are able to distinguish pretty well between just fluctuations and true bubbles, with the small error of 5 to 8%. You can generalize the estimator to include time. So instead of counting the number of bubbles at a particular separation, we also we expand our search volume in the time direction, and we count how many bubbles are at a particular space-time interval away from our reference. And the result is shown in this figure here. Once again, the correlation length persists to a few times the critical bubble size, but we also have a correlation time, which is of roughly the same order. What is noteworthy here is that while the initial state, the vacuum state, is Lorentz invariant, it's a relativistic field, our two-point correlation does not preserve that that Lorentz invariance, and this has to do with, of course, the fact that our detectors work in the lab frame. And here are the three combinations of parameters that describe the potential and the field amplitude, and the correlation persists in all of them at the same scale. I talked about how this can be implemented in a lab. This work was done several years ago, mainly in these two papers here. And what they show is that we can obtain the exact potential that we've been working with, the sinusoidal potential modulated by the parameter lambda, starting from a two-component Bose-Einstein condensate system. So if you you start from the GPE equations, you switch to polar bases, you integrate a few things, you get the equation you get a Stein-Gordon equation. Now, allowing this one parameter here to vary in time, you can create the false vacuum where the depth of the potential of the false vacuum wall is modulated by the lambda here. And this experiment is being built in Cambridge by Zoran and his team. Okay, so I'm a theorist. This is how I think an experiment like this could work. We're back to our video here. The first thing we need to do is we need to investigate exactly what the properties of the bubbles are, the bubbles that appear in the experiment. So a few things that would be very interesting to check if they match even the Euclidean instanton formalism would be the shape of the bubble as it grows, or the critical radius at nucleation, the rate of expansion during that accelerated expansion stage before it reaches the speed of light, and of course the decay time scale. So if we wanted to get the correlation function, we could take snapshots of this experimental setup during the phase transition. So while the bubbles are just beginning to form, we can, averaging out, inferring time backwards. We would like to infer the critical bubble nucleation coordinates in the same way that we did in our detection algorithm. Having those nucleation sites defined in this way, we could compute using the same estimator the correlation function between these nucleation sites and ensemble average to produce the full curve. Right. So this experiment would not only confirm first of all, what it needs to confirm is whether this truncated Wigner approximation is reliable. This experiment would even help us understand, develop a physical intuition of how vacuum decay works, since well, as far as I know, we only have some mathematical tools to do that. If these approximations that go into all of this work are reasonable, then we can think about measuring this two-point correlation function, and then see whether indeed the two-point correlation function is able to trace the statistics of the original of the underlying field. That is, to recover the power spectrum of the vacuum field and so on and so forth. So this is indeed a very, very exciting prospect. Okay. Again, the simulation, because it's really pretty. So here you see bubbles that grow and then take up the entire available space until the transition is complete. Right. So to summarize, inspired by galaxy biasing, we computed the 2-point correlation function between bubbles in this real-time phase space approach that was developed recently, and we were able to show that indeed bubbles can act as tracers of the underlying vacuum field in this process of vacuum decay. And if 2-point functions are a feasible, observable in experimental settings, then this entire pipeline would applied to the experimental case would teach us a great deal of physics that can confirm or not some very, very interesting phenomena. Okay, that's it. Thank you very much for listening.
Thank you, Dalila. That was very nice and very nice presentation, very clear.